Hi everyone, today we're going to talk about the proof by induction. This is kind of a very simple mathematics theory. I'm just going to separate into separate steps, and once you understand each step, then you can combine together and it can apply to any kind of the formulas. You can prove any kind of result. Hi everyone, today we're going to talk about the proof by induction. This is kind of a very simple mathematics theory. I'm going to separate into several steps. Once you understand each step, then you can combine together and apply to any kind of formula you want to prove. So before we start, the step 1 is write your equation in math formula. Before we consider how to convert your equation, we have to introduce a new concept. This is kind of simple. This is sigma. So the number above the sigma is the last value of m, and the numbers below the sigma is first value of m, and the 4n is the formula for the term. So once you understand this concept, it's very straightforward to convert the formula that a professor provided to us to the math formula. This is what they look like after we convert it. So here comes to our step 2. Determine the base case value. This is a definition of how we can determine the base case value. Since the base case value must be greater than 0, the base case value will be set to the next integer after 0. So we want to make this example very simple. We just set the n equal to 1 as the base case value. So after we determine, here come we to our step 3. Found the population Pn to be proved for all n larger than 0. So we just want to net the Pn equals to this formula and equals to this formula for any kind of n number larger than 0. And then we consider the following properties. The first thing is we have to consider the base case. Since we already set n equal to 1, so we want to prove that P1 is true. After that we approve that P1 is true, then we can consider the inductive step. So that means for all integers n larger than 0, if Pm is true, then Pm plus 1 is also true. If the above the properties is also true, then for each n where n larger than 0, the statement Pn is true. So consider the inductive step. I'm going to give you a simple example to help you understand this concept. So this means 1, 2, 3, 4, 5, 6, 7, 8. So what this means, if Pm is true, then Pm plus 1 is true. So let's assume that P1 is true. Then the P1 plus 1 is also true. That means P2 is true. And then like P2 plus 1 is 2, 3 is true. And you consider all the way to the end. That means all of the cases we consider is proved to be true. Then the process, that means the whole formula can be also be true. Then we come to our step 4. Substitute n equals to 1 into Clem to verify the P1. That means that we have to consider or prove the base case is true. So substitute n into this formula. So k is to n is equal to 1. So that means 1 plus 1 is equal to 2. 2 times 1 is 2. And then this formula n equal to 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 times 3 is 6. 6 times 1. And 6 times 1/3 is 2. So simplify both sides to check for validity. We also calculate that. It's 2 times equal to 2. So therefore the base case is true and the inductive step can be taken. So let's come to the step 5. Begin the inductive step by stating the induction hypothesis. So begin the inductive step by assuming that Pm for some integers m larger than 0. So you just replace the original formula n equals to m. So that means 1/3 m, m plus 1, m plus 2, right? And then come to our step 2. Consider the case of n equals to m plus 1. Separate m plus 1 term from the summation. Here's what we do there. So This formula that means 1 plus 2, 2 plus 3, 2 plus 4, 5, 6, 7, and then we plus all the way to the m, and then we plus m plus 1. So this kind of thing is considered represents 1 all the way plus m. And this one means m plus 1. So we separate it. We just put this m plus 1, just like there. We put Sm plus 1 into this formula. And we get this kind of number, right? And then we get this kind of like a formula. Then we come to our step 7, apply the induction hypothesis. Apply the induction hypothesis by replacing this kind of formula, these things with 3/1/3 m plus 1, m plus 2, and we get this kind of formula. Then we have to simplify and restructure the result. So first one, we simplify the result. It's just meaning you just do the calculation. It's very straightforward. And then we do the second step, restructure the result. Then we have to re-express the result in terms of m plus 1. So that means you have to reduce any kind of like formula and as possible as I can to replace with m plus 1. Okay. And then come to our step 9, show Pm implies the Pm plus 1. How can we do that? Okay, we just found out after we refactors. So after we refactors, we found that m plus 1 is equals to m. So that means also you can see that. So that means 3m, m plus 1, m plus 2. That may also implies the m, and when k equals to 1, the m plus 1, the k times k plus 1, 3 times 1, m plus 1, m plus 1 plus 1, and m plus 1 plus 2. You can also say, you just imagine that m plus 1 is equal to m. So that means this formula implies that this formula is also true. So therefore, the induction step has been verified. So the step 10, we can lead to the conclusion. Therefore, this formula for m larger than 0 has been proven to true. And I hope everyone can understand this concept and enjoy your. Thank you for listening to my presentation today. Thank you.